This conference will now be recorded.
Very good evening, students. As we were discussing Coulomb's law, so we had already discussed what is Coulomb's law in free space and in dielectric medium. Okay, and also we had picked up few problems, numerical problems. So among them, this was this, like one was this: C charges Q1 is 1 microcoulomb. This is Q2. This is Q3. Minus 2 microcoulomb and 3 microcoulomb. These are placed on the vertices of an equilateral triangle of side 1 meter. Find the electric force acting on charge Q1. So this was one question what we have already discussed. So I had actually discussed two methods. First method, like method 1, we had already discussed and found out the answer for this. You can see the previous lecture. And the second method we started but we could not complete it. Today we'll actually complete it again. We'll clarify a few points in that first, and then we'll proceed for today's topic. Excuse me. So what was the first method? First method was that, see, we have to find out force between 1 and 3. We have to find out force between 1 and 2, and then take the factorial sum. So when we take vector sum, then direction is also important. Like, see, in this case Q1 is positive, Q3 is positive, so the force due to that will be in this direction. Okay, so I can say F13 this way, and force on 1 due to 2, I can say that is in this direction because it is attractive force. So Q2 will attract this Q1 charge, so this is F12. All right, so the resultant will be along this direction. So this will be the resultant, and see, we know we will be using vector formula in this case. Say magnitude of this force will be square root of F12 whole square plus F13 whole square plus 2 F12 F13 cos of the angle between them, and this angle is actually 160 degree, sorry, 120 degree, that you know very well. Okay, because this is equilateral triangle, this is 60, and so it is a 180 minus 60, so that will be what? That will be actually 120 degree. Okay, so now yeah, excuse me. So if we do this, we'll get the answer for this question, and we had already discussed that. So today what we are going to discuss is the second method. So in that second method, actually that is kind of vector method. Okay, so second method we'll discuss today, method 2, to solve this problem. Okay, so what is that method? We'll just think that this Q1 charge is at the origin of Cartesian coordinate XYZ, Cartesian coordinate system XYZ, and we'll just try to give coordinate of these points. Okay, see, this point charge, it is, see, 1 meter, because the side Q1 Q2, this distance will be 1 meter. So this has got coordinate, x is 1, y is 0, and z is also 0. This is 0 0 0. And what about this? look, it has coordinate, x coordinate and y coordinate both. Y coordinate is the height, and x coordinate is nothing but half of this actually. So this will be 0.5 meter. So x coordinate is 0.5 meter, and y coordinate will be root 3 by 2 a square. I think root 3 by a, something like that. So we can just do it here from right angle triangles. Okay, this I have to find out. So this is 8, this is a by 2, this is a. So a square, see this is equal to a square minus a square by 4. So this will be kind of 3a square by 4. So I think I was right. So it is root 3 by 2a. Okay, so root 3 by 2 into a is approximately it is 1 point, approximately that will be 0.87, because see, root 3 means 1.373 1.731 or 732 kind of that. So divided by 2, so it will be coming around 8.7 meter. Okay, and z coordinate is 0 because it is in the xy plane. So this is how, once we can write down the position vector as well. Okay, we can write down the position vector. So I say position vector for this is r1, this particle. So that r1 has magnitude 0 obviously. So I say this is r2, this has position vector r2, this has position vector r3. Okay, r3. So now look what I have to do. I have to calculate force one, two. That means force on this due to Q2 charge. So what we can write here, we know magnitude Q1 Q2 by 4 pi epsilon naught into R1 minus R2. This is mod anyway. I can write R2 minus R1 also, doesn't matter since it is mod. So this will be R cube. If I write in terms of vector, this will be vector. Okay, so this will actually give you this force. Okay, and another force we have to find out is that this. Okay, so here also q1 q3 divided by 4 pi epsilon naught modulus of r1 minus r3 whole cube, and this is r1 vector minus r3. This is also a vector. Okay, so this is the thing. Now you might be thinking what to write in place of r1 minus r2 and what to write in place of r1 minus r3. So that's the point, crucial point over here. Q1 q2, anyway q1 magnitudes are given, so we can just put it. Obviously we'll just go ahead and do. Let me first find out f1 to force. So we know this is q1 q2 divided by 4 pi epsilon naught r1 minus r2 whole cube, and this vector r1 minus r2. Okay, this is one thing. Here, first of all, let me find out what is r1 minus r2 vector. Okay, then we can take the mod of that. So what is that vector? R1 minus R2. So we can find out actually. See, if we know 2 points, this is distance, right? If I go with vector also, it is actually, see the difference between these two coordinates. Okay, the 0 0 0 and this point is 0.0 0 0 0.5 0.5 and 0 0. So what we get? See, x coordinate 0 minus 0.5. I cap. Okay, this is whole into I cap. Then 0 minus 8, sorry, this is not the case. Other things are 0, 0, 0 because it has coordinate 0, so it has only x coordinate. So this is 0, this is 0, so this is actually minus 0.5 I cap. This is r1 vector minus r2 vector. So this is the thing. And now if we get mod of that, then obviously this will be just 0.5. That's all we'll have. Okay, so we have 0.5 and this is 0.5 I vector with a minus sign, obviously here with a minus sign vector. So what we are getting here for the force F1 2, F12 is F12 is equal to, see, 1 is 1 microcoulomb into 10, so 1 into 10 to the power minus 6, 2 is minus with a minus sign, 2, microcoulomb, this is 10 to the power minus 6 again. So Q on Q2 by 4 pi epsilon naught, this I'll put as 9 into 10 to the power 9 nearly, and this is 0.5 mod, so this a cube of this. So this will give you a value, and obviously the vector I have not written. Vector, see, I'll write it here. There will be vector, this vector. That is nothing but this one. So ultimately, what is the result we are getting for the force? If you just do the calculation, what you get is 1.8 into 10 to the power minus 2 I cap. Okay, I cap, and this is in Newton. All right, so this is in Newton. So what we get F12, I'll just write it here so that I can, oh sorry, so all right, so that we can erase some part. Okay, so you can see we get this value as like we get this in terms of vector only, this in terms of vector. So how much we are getting? 1.8 into 10 to the power minus 2 Newton. Okay, this is the actually this is all right. This is along x direction. This is along x direction. Okay, I cap direction. All right. Similarly, if we go for the other force, then also we'll just take care of these coordinates and find out the position vector and magnitude of that, etc. And it will be see if 1,3, this vector will be, if I do in the similar way, like I'll just write this one Q1 Q3, this is R1 vector minus R3 vector, okay, divided by 4 pi epsilon naught R1 vector minus R3 vector, and this will give you, you know how much this will give you? Minus 1.35 I cap minus 2.349. This will be in the J cap direction. whole into 10 to the power minus 2 Newton. Okay, so these are two forces. Now what we need to do, we need to just take the resultant of that. So the F will be F12 plus F13. So F12 we have already got this, and 13, this is in I cap direction. Let me just give the direction. I cap, and this part is also there, so minus three four nine j cap into 10 to the power minus 2. So if we solve this, how we get and what we get vectorially, what we get actually is that this is 0.45 I cap minus 2.349 j cap, and along with that there will be 10 to the power minus 2 Newton. So this is the force on the particle at A, Q1, sorry, Q1 particle due to this 2. Okay, so this was the brief recapitulation of what we had done in the last class and what we had to clarify. Okay, so it is said that if you give this IJK etc., you should not give any direction further. All right, I hope you have understood this. Now we'll go to a new problem. So that is also related to this Coulomb's law, but we'll be using Lami's theorem to solve this problem. So that's why I'm showing this Lami's theorem. Excuse me, just a minute. I'll just drink some water. Excuse me. So I'm back. So let us recapitulate a little bit about the Lami's theorem as we had discussed this, in the last class. What is this saying is that if there are three forces, and they are in equilibrium, three forces are concurrent forces. Obviously, they are passing through the same point. Okay, they are acting at the same point. So those forces are called concurrent forces, which are acting at the same point. So if there are three concurrent forces, as you see here, F1, F2, and F3, they are concurrent forces. They are acting at the same point. Okay, and this alpha, beta, gamma are the angle between any two forces, and you can see alpha is between 2, 3, beta is between 1, 3, and gamma is between 1 and 2. So if they are in equilibrium, that means the vector sum of the forces will be 0. At that situation, Lamy says that modulus of the force F1, so ratio of the force and the angle between the other two forces. So sine of the angle between the other two forces. Okay, if you take the ratio like that, if you take the ratios for all three forces, then those ratios are actually equal. So I can just demonstrate for you. So F1 is the force, magnitude of the force here. So the angle you have to take, see, if it is F1, then I have to take the angle between 2 and 3. So it is alpha, so sine alpha here. So I have to take F2, modulus of F2, then I have to take the angle between other two, this 1 and 3. So sine gamma, sine da here. And this is F3, so I have to take the angle between 1 and 2, that is gamma, sine gamma. So this is how we need to take care of this theorem, and we can apply for solving problems, etc. So I'll just show you how to apply for a numerical problem. So in this problem, it is said that two identical balls, each having a density rho, are suspended from a common point by two insulating strings of equal length. The situation is something like this. So you can see there are two balls. So these are two balls. Obviously, will actually in the problem itself it will be stated that this is a charged ball. Okay, charged ball. Both balls have the equal mass and charge, equal charge. And in equilibrium, see, it is saying in equilibrium. In equilibrium, each string makes an angle theta with the vertical. So this is straightforward. So this is the vertical line, and each string is making theta. This also will be angle theta. In equilibrium, this is in equilibrium. Now both balls are immersed in liquid. As a result, the angle theta does not change. If you just put all this system itself, whole system like the balls in some liquid, the angle theta does not change. Density of the liquid is sigma. What is the density of this material of the ball? That is rho. It is given in the beginning, and now density of this liquid is sigma. Find the dielectric constant of the liquid. So you have to find out the dielectric constant of the liquid. See, to solve this problem or to find out this dielectric constant, what you need to know? You need to know that if there are 2 point charges, Q1 and Q2 they are acting through this line, like along this line, and if the intermediate medium is air, so in that case only we have seen that the force, coulomb force, will be Q1 Q2 by epsilon naught r square. So this epsilon naught is actually representing the air or vacuum. Now if the whole system is see, all these two charges are immersed in water or some other liquid, then how this changes? So it will change here. Q1 Q2 I had discussed yesterday. So this is not epsilon 0, this is epsilon. So epsilon means epsilon 0 into epsilon r, and this is the situation. So Q1 Q2 by epsilon 4 pi epsilon naught r. So r square is already there. So look, in this case, this is different than the original force. See, this is F prime if I say. So what I said here, that when the charged particle is inside the medium, dielectric medium, then this is the force, original force in vacuum. Now dielectric medium, it will be actually divided by the dielectric constant, okay? Dielectric constant or relative permittivity. Okay, so we have to find out this F prime by F. So what we need to do, we need to find out, if we want to find out the dielectric constant epsilon r, then we have to do F prime, Fe prime divided by Fe, electric forces. Okay, so I think I have given some clue. Now we will proceed for solving this problem. Let us see the situations, both the situations. See, this is inside liquid. Say inside liquid. So when it is inside the liquid, as I said, the forces will be altering, right? Or the value will be modified. Okay, first of all, let me tell you what are the forces acting. If I just consider the forces on a single particle, okay, just single ball. Okay, so this ball is actually pulled by the tension along this direction, and that tension has made an angle theta with this vertical which is passing through the ball. Okay, okay. Now what is this? This is the weight of the ball, and this is what? This is actually a repulsive force, since these two charges are same and they will be repelling each other, so this force will be repulsion force. Now this system is in equilibrium. So if it is in equilibrium, see, in this case you can very much understand that there are three forces, this Fe, W and T. Can we apply Lamy's theorem? So we can directly write Lamy's theorem for this, but let me first make you aware that the same thing is kept now. One, it is done in air, and another one, it is done in liquid. So when it is in liquid, so W will be W minus W prime. Sorry, W will be something else, not the exact value of the weight, because the liquid is there, liquid will have some buoyancy force. So W prime, and this is Fe prime, this is T prime. Okay. Now if we write the Lamy's theorem or apply Lamy's theorem here, so what we get? We can find out the forces like dielectric constant here using Lamy's theorem. Let me write this Lamy's theorem here. See, if I consider these two forces alone in this case. See, if I write W, see, Lamy's theorem says W means this force, you have to take the angle between these two. W by 90 plus, so W by sine of 90 plus theta degree. Okay, and what we take? We take Fe. Fe means this way. So Fe, when I take, then according to Lamy's theorem, I have to take the other one, the angle between other one, this one. So it is 180 minus theta. Okay, so these are the thing. Now look, for these two forces, I just want to do little bit of, I think I have done some mistake here. 90 plus, so 90 plus theta. This should be the case. Because W is here, so I have to take this angle. So this is 90 degree plus theta. All right. So this is actually cos theta. This is, I'm sorry, this is 180 minus, this is sine only. This sine, so sine theta. Yes. Okay. So similarly, if we write for this system when it is inside liquid, so inside liquid, if I write the same things, so this will be W prime by W prime by cos theta minus Fe divided by, here also Fe will be Fe prime actually, since all the forces will be modified. Fe prime divided by the angle. Okay, so this is sine theta only. So look, if I just take the ratio of these two equations, what we get, actually we get W by cos theta, okay, Fe by sine theta. This is one. Second thing we got W prime by cos theta. So this is the thing. Now we can just do one thing. We just take the ratio. So W by W prime or W prime by W, and this F by F prime. Okay. So from here we'll be able to find out actually. So W prime we have to find out. W prime is equal to W into F prime by F. So this F prime by F. Look here, what we have done. F prime by F is actually C. Okay, so if we just put the value of F prime and this F, then you get actually the value of K. Okay. So this is K. This is F E prime is equal to F by K. So f by f prime, sorry, f by f prime. It should be k should be f by f prime. So this should be actually w into 1 by k prime. K. Okay, so we have to find out actually k. K means w. So w by w prime, we can actually we have few more steps to go for the answer. So what we have got? We have got the dielectric constant is the w by w prime. What is this w? W is the water content in the volume, okay, into g. So rho vg. What is this? This is actually this w actually is, you know, w prime is w minus uh, up. This is bind supports actually bind support. Okay, bind force. So how do you get bind force? So we will get actually this rho vg w rho vg, and this is actually see w rho, sorry, rho vg minus this will be sigma vg. Okay, if we take this common, because this is the displaced water, volume of the displaced water, so this is the mass, and see this is the bind force, mass loss due to bind force, and this, so it is actually see vg will cancel from each, so you'll get rho minus sigma. So this will be the value of dielectric constant. Okay, so this will be the answer for this question. I hope it is clear to you. So we'll go to the next problem. Now we have actually somewhat discussed about Coulomb's law. We'll just now go to the next topic called electric field. See, if you have a charged particle, if you have a charged particle, point particle Q, okay, and you bring some charge near to this, suppose this has some area in between, if you bring one unit charge also, then what it has been observed is that this charge will be experiencing a force in this region anywhere. Okay, so you know these two charges will not be able to interact each other. Okay, so what is the case? The case is that charged particles cannot interact with each other directly. What does this mean? This Q1 and this Q2, we are calculating forces, that is fine, but here interaction means one will experience force due to the other, so that is called interaction. So this interaction cannot happen directly, but how does it happen then? So it is thought that charged particle, see, if it is charged particle, positive charged particle, it will create a field around it. It will actually create something which is called field, electric field, something called electric field. and that electric field will actually exert force on the test charge. Okay, so charge particles individually, they cannot interact with each other. They interact with each other with the help of the field. Field means what? If a charge particle is here, point particle, if you have point charge particle over here, there will be certain region within which the effect of this positive charge will be persisting, and any charge you bring at any position, then it will experience a force. So a charge particle creates something called an electric field, and this electric field will exert force on the second charge particle, and thus two charge particles will be interacting with each other. Okay, so I hope you have understood the concept of field. So a charge particle will create its influence, I can say its influence, and that influence is called actually the electric field. So formally, if we define electric field, how do we define formally? The region surrounding a charge particle or a distribution of charge particle is called field. So any charge particle you keep, so from there, from the charge particle around it, there will be a region around it, which, like within which any charge particle will experience a force if we brought there. Okay, I hope I have made this statement clear. Let me just give you the figure or representative figure. So like suppose there is charge plus q, so it will actually create a field around it, and it has spherical symmetry as well, so we can go with this. So it will create a field around it. This is called electric field. And this electric field, when I bring a charge over here inside anywhere, any place, it will actually exert a force. That force is actually the force we see between two particles. Okay. All right. All right. So this is field. Now see, electric field is actually a vector quantity. We'll discuss it later also. So what is electric field strength? Just like gravitational field strength, electric field strength is also the similar thing. So the total is the field, electric field, and electric field per unit charge, unit positive charge is called field strength. Okay, so what is field strength? It is the field itself, but how it is, like how, why we have defined this? So look, electric field strength is the force. Actually, I can tell you one thing. So if you bring a positive charge, positive unit positive charge, it will actually experience a force, repulsive force, due to that charge. Okay, due to that field. All right, so here you look, electric field strength is actually force per unit positive charge. So you might be thinking what kind of definition it is. I'll give you the statement. If I have, let me just check whether I have the statement here. No, I can see actually there are two charges. They will actually repel each other with the electric field, respective electric field. So any charge particle you bring in an electric field, uniform electric field, if you have a charge particle like this, and if it is positive, then there will be a force on this charge particle due to the field, and that will be acting in the direction of the field itself. Okay. So electric field actually is the force per unit charge. Suppose there is a charge or charge distribution, maybe charge Q, let us take. It is actually creating a field around it, so this is called source charge. If it is creating a fold around it, like field around it, then that particular charge is called source charge. The charges which are creating field around it, and the charge which is brought at any point of that field is called test charge. Okay, test charge. So electric field is actually Coulomb force. It is denoted by Coulomb force for a point charge, Coulomb force. So Coulomb force by charge Q0. So this Q0 is the test, sorry, the test charge. It is called test charge. This is test charge, and the charge which is creating this field is called source charge. Okay, I'm sorry, this is test in the sense examine, test charge. And in this case, few points to be remembered, like we can remember a few points. Q0 must be infinitesimally small. Q should be very, very small. Okay, that should be very, very small. If this is very, very small, then the source charge will be not disturbed by this test charge, and the field due to that will be equivalent. Okay, so this has to be very, very small or infinitesimally small charge. So that's why this limit Q0 tending to 0 has been used. Okay. Now field could be explained. Sorry, field could be found out for various charges or charge distributions. So we'll try to see something. So this electric force, as I said, it is electric field is field strength is a vector quantity. It is a vector quantity, and it is, say, for a positive charge, it is acting in the same direction. Okay, so see, if you have a charge capital Q, it is creating a field around it. Okay, around it, and there is a field Q, so some charge, let us say some charges, let us say it is Okay, let us say Xi. So I'm sorry. So it is said that electric field leads to a force. That means if you keep a charge near to this field or inside this field, suppose you have a uniform electric field at any place, if you place or bring a charge Q0, it will be experiencing a force. If it is positive charge, then Q0E in the same direction as the field. These are the direction of field. If the charge is negative, then the force will be in this direction. Okay, this will be Q0E again here. So this is force. So electric field leads to the, this is field, leads to the force. Okay, so how to find out this field? First of all, how to find out field? How to find out field? So it is actually found out from Coulomb's law itself. Because we have defined that electric field is force per unit charge, right? Sorry, force per unit charge. Force per unit charge. And what is this force? Force is actually Coulomb force. And what is the direction of field then? Along the direction of Coulomb force itself, its direction. Okay, so I think I'll stop it here for today. Next day, we'll take up numerical problems on electric field. So thank you for your patience. Bye for today.